Okay, good morning, everyone. Welcome to the GIS Sea Level Rise seminar. We're very glad to have Dr. Abbas Khan here today. He is a professor in the Division of Geodesy and Earth Observation at the Department of Space Research and Technology at the Technological University of Denmark, DTU Space. And his research focuses on utilizing observational data, in particular geodetic data, to study changes associated with glaciers and ice sheets, with a focus on the Greenland Ice Sheet. Prior to his current position, Dr. Khan was a senior scientist and research scientist in the same department where he is now, and he earned his PhD in geodesy and bachelor's and master's degrees in geophysics from the University of Copenhagen, Denmark. And today he will be speaking on the topic mapping changes in the Greenland ice sheet margin of the past century using airborne and geodetic surveys. So welcome, Abbas.
Thank you. Okay, do you see my screen now?
Yes. Looks
So before I start, I want to acknowledge my co-author. It's Christian Kelsen. He's from GEOS in Denmark, and Kurt Kjær, he's from Globe Institute, University of Copenhagen, and Anders Bjørk, he's from IGN, University of Copenhagen. And then we have Danielle and Valentina. They are also both from DTU Space. Now, this talk, it will focus on mass change from the Greenland ice sheet from 1900 to 1980s. And for some glaciers, we can estimate annual changes. And for other regions, it's more long-term changes. And next, I will focus on satellite altimetry, and it is monthly products. And last, it will be daily products or daily mass change from for the entire Greenland ice sheet, and that is based on GPS data. And finally, a conclusion. Now, before I start the presentation, I just want to say that also so you have a background in the data I'm using. Most of this data, it comes from a Geodetic Institute. So it was the Geodetic Institute, they were responsible for all the surveys in both Greenland, Faroe Islands, and Denmark concerning mapping and gravity measurements and all other geodetic measurements. And in 1988, they changed the name to KMS, the National Survey and Cadastre. And I started in 96 working for KMS. And after some years, in 2005 or in 2004, we split it into two divisions, one called SDFI and DTU Space, where I'm working now. But DTU Space is still responsible for all the, for instance, gravity measurements in Greenland and all the GPS measurements in Greenland. So this is a map of Greenland. It's a typical map which shows the ice sheet, the land areas, and so on. And next, I will zoom into the region here that I have highlighted. So this is a sketch, and this is actually a sketch which can be very useful to map position of past glacier history. This is from 1853, and this one is created by Henrik Johannes Rink, and the glacier up north here, it's also named after him, Rink Glacier. Further south, we have Jakobshavn Isbre, which which I guess everybody know very well. Rink, he spent a lot of time in Arctic region and in especially in Greenland mapping. So where he mapped both the west coast, south coast, but also the east coast. And it is products like this that we can use nowadays to say something about where was the ice margin, for instance, back in 1853. Now, if we zoom into this region here, this is Jakobshavn. So it's the same map as I just showed you. It shows the Jakobshavn and the Jakobshavn ice stream. Jakobshavn now, it's called Ilulissat. And if you look at the margin here, uh, it is actually very well mapped, taking the conditions into account that they were at that time. So here we see where the front is in 1850 and 1875 and so on. And so the data that we are using from 80s to 1920s, it is mainly based on sketches and mapping, and also from photos. From late 19th to now, we have many more aerial photos, which gives a much better picture of the front positions. So for Jakobshavn, in this case, the front has retreated by more than 40 kilometers over the last 120 years. This is a paper. It was published in 1935 by Niels Erik Nordlund. And Niels, he was the director of the Geodetic Institute and also professor. He was a mathematician, and he wrote this paper. And if we look at the text here, it says that the Geodetic Institute, they were conducting surveys on ground while they got help from the Danish Navy. They lended a seaplane. So it was a combination of survey on ground, but also aerial photos. The survey on ground, it was, for instance, made by conducted using theodolite, and you can also have a more modern version of theodolite, and they are used to map distance between points and angles. And the map here with all the red dots, it shows fixed points. And if you go to Greenland, you will see markers on ground. And they are still there, and we still use them as fixed points. But yeah, in the old days, it was using triangulation, but now we simply use GPS. Now, in the paper, they used the aerial photos, and this is an example of aerial photos. So this is the survey they conducted in the 1930s, and it was mainly the west coast, the east coast, and all the way up to Danmarkshavn in northeast Greenland. So while they conducted all these aerial photos, they will also achieve on-ground mapping points and distances. So this is the survey in 40s. So each dot here, it denote a photo. So it's a lot of data. And this is from 60 to 70s and so on. And the most recent, it's from, it was conducted between 78 and 87. And now, of course, as you know, we use satellites, so there's no reason to go up there and do the aerial surveys again. In the 1930s, so this is from the East Coast during one of the missions. So in this mission, it was led by Lauke Koch. And Lauke Koch, he was, so you can say that he was a person responsible for the aerial photos, and while Nils, he was responsible for all the ground measurements. There's actually the region here called Nordlund Alps. It is named after Nils Nordlund, and it was Lauke who named this region Nordlund. So, and yeah, this is the airplane on board the ship. So, yeah, they are preparing the airplane. And yeah, Lauke Koch, he also had his wife with him on this trip. And the trip lasted a couple of summer months. And so they are preparing to conduct aerial photos. And as you can see, they are all wearing polar bear outfit. So this is a photo, and it's approximately at 5 kilometer elevation. You can see the mountain tops in the background here. And so here's an example of the difference between retreat and thinning of the glacier. So the first one here is from Laukokok mission in 33, and the second image is from 2013. It's from Kurt Kjær, who flew exactly at the same positions as they did in 33, just to make the comparison. And you can also, in the new photos, clearly see the trim lines. And this is another example. So this is also from southeast Greenland, where you can see the glacier has retreated approximately 20 kilometers. Now, let's look at some results. And to start with, I will focus on Jakobshavn Isbræ, Kangerlussuaq Glacier, and Helheim Glacier. So, we use a combination of trim lines. So that's a boundary between the region with vegetation and no vegetation. It's very clear on all photos. And we also, of course, use all the historical images, aerial photos, and also over the last two decades, we use satellite data. This is an example of elevation of a digital elevation model based on one of the old photos. So this is for Jakobshavn from 1964. It's actually photos with very good and high quality. So you can also really see the icebergs in the fjord in front of the glacier. So we have merged all this into so in this case, it is elevation models. So from 1875 to 2013, we have elevation models, and you can see the glacier retreating. Of course, we do not have observations for each year. So if there are a 10-year or 5-year time span with no observation, we just simply do a linear fit. And this is an example for Kangerlussuaq Glacier in southeast Greenland. So from Little Ice Age maximum until 1981, this region has thinned, or front of the glacier has thinned about 240 meter or 260 meter. So it's a lot of thinning before we started using satellite data. And so here you can see both Jakobshavn retreat and also the elevation change or thinning of Jakobshavn, and it's in the from 1900 until 2012. We are talking about the thinning in the order of in some locations 700, 800 meter, and it's the same for Kangerlussuaq Glacier. While for Helheim Glacier, that's the bottom panel here, we don't see that much thinning. It's much less, and also the retreat of Helheim, it's very limited. It's we are talking about a few kilometers. Now, all this thinning, it causes a lot of unloading. So this is the total mass loss for Jakobshavn, Kangerlussuaq, and Helheim. So for Jakobshavn, it's more than 1,000 gigaton over 120 year, and it's the same for Kangerlussuaq. For Helheim, it's much less. The blue curve, it denotes mass change due to SMB, and in this case we use a model from JSON box. So what we see here is that the thinning and mass loss, it is mainly due to ice dynamics. Now, all this mass loss, it also causes land rise due to unloading, and for Jakobshavn, we have elastic uplift. So this is the total elastic uplift over 120 years, and it's 210 or 2.1 meter for Jakobshavn, and Kangerlussuaq, it's approximately 2.7 meter. So we are talking about meter level of land rise. And on the other hand, when we have this ice loss, water is moving away from the glacier. So the water level here, it is for Jakobshavn, it decreased by half a meter. For Kangerlussuaq, again, approximately half a meter, and in the order of 10 centimeter for Helheim. And if we also take the GIA effect into account, and so if we look at all the three contributions, then we have a relative sea level change. So if we are standing next to Jakobshavn glacier front, then we will experience a sea level drop of 2.2 meter over 120 years, or for Kangerlussuaq, it's in the order of approximately 5 meter of sea level drop. And using GPS, we also see the similar effects. So GPS suggests, now, of course, these GPS measurements, they are only over the last 15 years, and they show land rise of approximately 25 centimeter. So in total, we have estimated contribution of 8.1 millimeter from the three glaciers, Jakobshavn, Kangerlussuaq, and Helheim. And next, I will look at the entire Greenland ice sheet. Now, it is very difficult to estimate annual changes over the last 100 years. So this is why we have only done it for three glaciers. It takes a lot of time. So for the entire Greenland ice sheet, this paper was published by Christian Kelsen. And for this paper, we have just one estimate for 1900 to 1983. And So the average mass loss for the entire Greenland ice sheet for this time span was 75 gigaton per year on average. And if we look at which region lost most ice, again, it's mainly northwest Greenland, but also southeast Greenland here. So this is a distribution. So here we have the loss between 1908 and 1983 and so on. And as you can see at the bottom here, we are talking about 75 gigaton per year, and then the number increases to approximately 180 gigaton from 2003 to 2010. The yellow bars here, they denote from result from Kjeldsen published in Nature, and then we have all the other estimates from altimetry and gravimetry and so on. And if we take a zoom, well, this figure it's outdated, but yeah, in 2012 we had huge ice loss, and the rate it has declined a bit since 2010, 11, 12 here. Now the next, I will talk about monthly estimates. So this is a more recent paper that we have submitted, and it will appear soon in Earth System Science Data. And in this paper, we use data from ATM, from ISAT, GrIS, and NVSAT. From NVSAT, it's a radar mission, so it's very difficult to get measurements very close to the ice margin. And from ISAT and ISAT2, we have much better coverage along the margin. So in addition to this, we also have cryosat data included in this study. And we have ATM. So here, now both this plot and this plot, there is, of course, more data than I show here. But what I show here, it is points where we have overlapping data, meaning that we are able to create a continuous time series, meaning that we are able to estimate the elevation change over 5, 6, or 7 years, or depending on length of the mission, and then we fit a polynomial plus a seasonal signal. So, and then we use for each month and from each mission estimate of the elevation change. Now, soon you will be able to look at the details about the method in the paper. So the idea is to merge all this data into one big pile and then interpolate over the entire Greenland ice sheet. And if we compare with other studies, so we compare with IMPI gravity data input-output method from Ken. Overall, it looks fine and consistent with other data. And so now I just compare with the gray, it is from altimetry product that we have just submitted. And then we also have gravity data here. It's from Valentina that she published in GRL earlier this year. And as you can see, there is a difference or a bias, and it's because in our study, the gray region here, we only focus on the Greenland ice sheet and not peripheral glaciers. Now, if we say that peripheral glaciers, they account for about 15% of the total ice loss that is estimated from GrIS. So then we get something which look like this. So I had just multiplied the GrIS estimate with 0.85, and so what we see here is that overall the trend looks fine, but also the seasonal signal between the two data product, it's very similar. For instance, here we have the huge melting and mass loss in 19 and also in 2012 here. So they both capture more or less the same signal. If we look at the spatial distribution, then the altimeter product, it suggests actually a thickening. So this is the total contribution over the last 20 years. So we see a thickening along the east, northeast region here. While, I mean, this is again due to resolution of GrIS, it suggests a thickening at the center of the Greenland Ice Sheet. So this movie, yeah, it shows the cumulative elevation change. Now the colors they shift from blue to red in the beginning, and that's because of the seasonal signal going up and down here. So again, we see it's mainly along the southeast Greenland here and northwest Greenland here, where we have the largest drop in elevation. So it's, for instance, Jakobshavn Glacier here. Now, next, I will focus on GPS data and the daily solutions. So this is a typical setup of a GPS station. The antenna, it is mounted directly on bedrock. So we really measure how fast the bedrock is moving up or down. And there are a lot of GPS stations now, more than 60 stations. And we, as a part of our geodetic survey, we visit all the stations at least once per year. And the movie here, it shows a typical station. And normally we put on a mountaintop. And in this region here, there are actually no trim lines, suggesting that the top of the mountain where we installed the GPS station, it was covered by ice in 1900. And in this region, we have uplift of approximately 2 centimeter per year. We do also run into problems, and this is typically polar bears. They cut our cables, and then we have to revisit the stations. And most of the time, it's just a communication. So we use Iridium, and if it's just a communication, then the data is still downloaded, or it is still locked, and we can download it whenever we visit the station. This is Kaga. This is a GPS station next to Kangerlussuaq Glacier. So now the method by Valentina, so she has developed, you can say, a function which use all the GPS data or time series from all the GPS data and convert land uplift into mass change. So the blue curve here, it shows mass change from GrIS, and the red curve, it shows mass change from GPS, or a combination of all GPS stations in Greenland. And it's almost perfect. There's almost a perfect fit between GPS and GrIS. And it also means that we can use GPS to go further back in time. So the first couple of GPS stations. They were deployed in 95. So using GPS, we can go back to 95 and say something about the Greenland Ice Sheet mass change. So the method here, it works for the entire ice sheet. So our next step is to look at the different basins. So for instance, we have in North Basin 1, in Northeast Basin 2, and so on. So in the first paper here, Valentina simply used vertical motions only. And the idea in the next step is to include horizontal displacements also. So the idea is to get to estimate a daily solution for the entire or for each basin mass change. And we are also trying to estimate mass change from a single glacier. And this is something we are testing at the moment. So for Jakobshavn, we have so the green dots here, Ilulissat and Kaka, it is stations that were installed in 2006. So we have all 20 years of data. The 4 red dots, it is new stations installed this summer. So the idea is to estimate mass change from Jakobshavn on daily basis only using GPS data. And the idea of putting 2 stations, one at the northern region here, close to the ice front, one at the southern region here, is that there might be a difference between what the northern ice stream is doing compared to the southern ice stream. Now here you can see this. So this is based on Arctic differences. So the first panel here, it shows mean elevation change from 11 to 16. And the second here, it shows mean from 16 to 19. And now we see the blue color here. This has also been reported by several studies suggesting that the glacier started to thickening near the front here, and especially near the southern ice stream. And from 19 to 21, it started to thin again, and over the last 2 years, it has actually been close to zero or maybe a little bit of thickening. Now, all this using a combination of both vertical and horizontal motion, we will be able to detect all this and these mass changes on daily basis. All this data, GPS, everything, it is freely available if anyone want to use it. And also the new data and the new stations that we have just deployed this summer, data is available. So in summary, from 1900 to 1983, the Greenland Ice Sheet, now it is excluding peripheral glaciers, contributed to 17.3 millimeter of global sea level rise. And from 83 to 2003, 4.1. And over the last 20 years, it's 12.1 millimeter. Where you also have the rates here. Now, the first panel here from 1900 to 1983, I say it's a minimum estimate. It's because in the paper published by Christian, we did not include all the ice loss that took place between the front of the front position from 1850 to 2003. So we used the 2003 front position as reference and then estimate what is lost from 2003 front position and inland. So all the ice loss from the fjord region here, not just for Jakobshavn, but also all the other glaciers around Greenland were not included. Okay, thank you.
Okay, thanks very much, Abbas. Do we have any questions? Yes, Jeff has a question.
Hi. Thanks for the talk. Is there any evidence from the photographic surveys of the large-scale melt of the Greenland Ice Sheet during the abnormal warming in the 1930s to 50s?
Yeah, there have been some publications from Anders Björk, which suggest retreat of glaciers both in southeast Greenland and northwest Greenland in 30s and 40s.
Can you estimate how much it is relative to the current retreat?
Yeah, well, it is. I don't remember the numbers, but it is mentioned in the publications.
Right. Thanks.
Yes, Klaus has a question.
How do you account for what ice is floating and what's floating the land where the grounding line is? Does that introduce a substantial uncertainty in some areas?
Yeah, and so this is why in the Kjeldsen paper we estimated mass loss from the 2003 front position and then inland, because we have a very good idea of what is floating and not floating. But on the other hand, if you look at Jakobshavn, for instance, it was 400 or 500 meter thicker. And based on the fjord depth, we can estimate what was floating and not floating, simply because we have a very sharp estimate of the trimline position, so the glacier elevation.
Yeah.
Yes. Any other questions?
Yeah, I had a question about your. I noticed that the altimetry data, the seasonal variability seemed to be a little larger than GrIS. And I was wondering if that might be due to like variations in density that you're not capturing.
Well, if you look at, is it this plot you were talking about?
Yes, I think so. Yeah.
Yeah. Well, taking the uncertainties into account, yeah, definitely, Fern, it does play a big role here. But in general, I would say it's within the uncertainty level.
Okay. Okay. We have a question in the chat from Vivian. Here's Vivian.
Yeah, my question is, if you included the peripheral glaciers, would you get a larger contribution to global sea level from Greenland?
Oh, yes, definitely. So when I say the total contribution is 23.5 millimeter, if we include peripheral glaciers, my guess is it will be close to 40 or 4 centimeter.
Mhm. Okay, great. And you've included the glacial isostatic uplift and that.
Yeah, all this is taken into account. Yeah. Yep.
Any other?
Yes, and any other questions?
Hi, this is Felix. Sorry, I don't know how to raise my hand. Can you hear me?
Yes.
Quick question. I dialed in late. I apologize if you explained this earlier. What role does uncertainty play? Your knowledge of the bedrock topography? And if you addressed it, you can just tell me. I can look it up later. But can you speak to that a little bit? The bedrock topography underneath the ice. Does this the knowledge of that, is that important for your analysis at all or not?
No, we're only looking at the surface and changes of the surface, and we use the changes of the surface to estimate mass loss.
Okay, so you don't need to invert for velocities where you need to have a knowledge of the geometry of the ice
We
sheet
don't.
underneath or the bedrock underneath. Okay,
Well, we don't use velocities here at all.
okay. Understood. Thank you.
Yes, any other questions?
Well, I guess we have no other questions. We could stop here
Yep.
for comments. Okay, so thanks so much, Abbas, again for coming.
Thank you.
And thanks everyone for joining.
Thank you. Bye.
Okay, thank you.